The next example is again pulling the chain example, but let me just say pulling the chain up example. There is a chain that is lying on a heap, in the form of a heap on the ground. So there is ground below, there is a heap, and then there is somebody who is applying a force P at the top end and is trying to pull this chain up like that, So let me define this problem. This is also given, and let at some time x be the height of the chain that has risen above the ground. So what do we need to find out? We need to find here first the force P that you will have to apply as a function of x. Now clearly this P will have to be a function of x, because as x keeps on increasing, to keep that ever increasing mass of chain moving at the same velocity up, your force will have to increase. So find P as a function of x. And second is a very interesting problem. It is asking you to find out the total energy lost during the lifting of chain. So how are we going to approach this problem? Again, you know that it's a variable mass system, because the system in fact, the part that you're talking about, it's being lifted up, so some links will keep on getting added to it and so on, and that's our hint. So once we know that this is a variable mass system problem, the equation that we need to use is summation of F external plus V rel dm by dt is equal to m dv by dt. And we need to define who is our main object. And I think in this case all of you will agree if I say that the main object can be chosen as this part of the chain that is moving up at a steady velocity v. So let us say, the main part is this red encircled portion. This is the main object. So if that is the main object, then what can we say about m? So therefore m is the mass of main object, and if the length is x, I know that they have shown x to be from there to the base of the heap and all, but then you don't go for that diagram. What you go for is that this x is equal to the total length from here till this place, the part of the chain that has been lifted up, or if you think of the height of the heap as negligible, then also you can do this, and we will have to take the height of the heap as negligible. We cannot take it as large, because if we take it as large, then the change in the gravitational potential energy of the chain will have to be found out in a more complicated manner. So let's assume that the total height of heap is negligible. Let us say that this height here is going to be negligible. If that is the case, then the total mass m of the main object becomes lambda x. This is the total mass of this main object. dv by dt, the acceleration of the main object, is 0, because the main object is now traveling up at a constant velocity. So that's 0. Okay, that's also cool. Summation of F external. This term should be calculated for the main object as well as for the small amount of mass that is going to be added to it. We know that in chain kind of problems, that small amount of mass is another link, that orange encircled link that will be added into the main object in a small amount of time. And right now that link is resting. So that small orange colored link has its weight acting on it and has a normal reaction acting on it. Normal reaction is because of that heap itself, and the net external force on that small orange colored portion is going to be 0. So I don't have to really take it, and in fact you will see that in most of the problems this F external will be just the force acting on the main object. We will be able to ignore other forces. So what is that F external? F external is, and for defining that F external, as before, I will take a coordinate system. So let me take a coordinate system here, people, where to the right hand side is my plus x axis and to the top is plus y axis, like this. So with this kind of a coordinate system in place, I can say that F external or summation of F external is going to be, now what are the forces? A force P is acting on this entire main object in the upward direction, so P with a J cap plus this portion's weight is going to act in the downward direction. So how much is its weight? Lambda x is its mass times g is its weight, and all that weight is in the minus j direction. So I can say this is P minus lambda x g whole thing j cap. That's the total external force. Okay, what is this guy VREL? So VREL now is going to be the velocity of this orange portion with respect to this red encircled portion, right? So velocity of added link minus velocity of moving chain. That's going to be the answer here. So how much is the velocity of the added link? The link which is being added has got 0 initial velocity, so this is 0 j cap in fact, minus the moving chain has got a velocity v in the upward direction, so this is v j cap, and you will get minus v j cap. This is VREL. And what is this guy dm by dt? In a small time dt, the distance by which the chain moves up is v dt, which is also the length of chain added into the main object or into the moving chain. So therefore the total mass added is going to be, the total mass which is being added is going to be v dt is the length times lambda, that's the total mass, and so dm by dt is going to look like lambda v, and I'm going to take that as positive. I'm going to take that as plus because this mass is being added into the mass of the main object, and so dm by dt is going to be plus lambda v. Now I have all the ingredients to be able to write this equation. So what will that equation look like? F external is P minus lambda xg. So now therefore I'm going to get P minus lambda xg times j cap here minus VREL. VREL was minus v j cap. Sorry, it's not a minus here, it's a plus, and minus v j cap times dm by dt is plus lambda v, every term with a proper sign with a proper direction, and that is all equal to lambda x times 0. I don't even have to bother about the term on the right hand side because dv by dt is 0, so I've got a 0 here, gone. So what is it? You can just rearrange this equation for p, and you will get p in magnitude terms as lambda xg plus lambda v square, and that is equal to lambda taken common v square plus xg. So this is the total force that you will have to apply at the free end in order to keep on moving the chain up at a constant velocity. This is the final answer. You will see that there are few components. You see lambda xg, that term shows you the total weight, but lambda v square shows you something else. Lambda v square shows you the amount of force that you need to lift up a small link and make it move up at a velocity v in a very small amount of time, you know. So this extra term shows that you will have to make some extra effort here. Then there is another part to this problem, the energy lost during the lifting of the chain. Let's also do it. For B part, let's see what is happening. Initially the chain was lying in the form of a heap on the ground, so maybe there was this huge heap and that's here, And finally what happened was that the chain was all lifted up. It was like this, it was like that here, and this is the ground, and this entire chain is moving up at a constant speed v. So this is the initial situation, this is the final situation, this is the beginning of the lifting process, this is the end of the lifting process. By this time all the chain has been lifted up. So let's try to figure out what is the work done by that external force P that we have just now found out. That's number one. Let's find out the increase in kinetic energy of the chain. Let's try to find out the increase in potential energy of the chain, and then let's see whether the numbers match up. So that's the first thought that has occurred to us. So how can we find out the initial kinetic energy? KE initial. Since KE initial was 0 because the chain was lying here, let me say this is initial, and here this situation is final. So since the chain was at rest on the ground initially, K initial was 0, and KE final was the entire chain moving with the velocity v. So half m, the total mass, so that is lambda times L times v square. Therefore delta KE is equal to, in fact, increase in KE. Let me just say increase in KE is equal to lambda L v square by 2. Let's keep that as equation number 1 here somewhere. Now, how about the potential energies? Let me take the ground level as the 0 PE level. So, since PE initial is 0 and PE final is, so finally how much will be the potential energy? I can find out the potential energy by thinking about the center of mass and its height above this ground level, so that will be L by 2. So m, the total mass, times g times the height of center of mass, and that's it. So lambda L square g by 2. Therefore increase in PE is going to be lambda L square g divided by 2. This is equation number 2. So I have found out the total increase in kinetic energy of chain, the total increase in potential energy of chain, and now I need to figure out what is the work done by this force. Now this force here, P, is a function of x. So the work done is integral P dx. So work done by P is equal to integral P dx. This is what we do for variable forces, which is integral of, and what is P? P is lambda gx plus lambda v square, lambda gx plus lambda v square times dx. And what are the limits on x? X is the amount of chain that was in air at any instant. Initially that's 0, and finally that is equal to L because the total length of chain. So 0 to L. Lower limit is 0 and the upper limit is L here. And then when I integrate, what do I get? The first term, lambda g x square by 2, where if I put the limit 0 to L, I'll get lambda g L square by 2. Done. So that's one term, plus what will be the other term? Lambda v square times x, and after I put the limits 0 to L, I'll get lambda v square L. So this is the total work done by this force P. This is equation number 3, and you see that they don't really match up. The increase in PE, that's lambda L square g by 2, and the first term, they will exactly match up, but the increase in KE is only lambda L v square by 2, while the work done term is lambda v square L. Oh, so there is a greater amount of work done and a lesser amount of increase in KE. That means some energy has been lost. So what is the energy lost? So therefore energy lost is lambda v square L minus lambda v square L by 2, which is lambda v square L by 2. So this is the amount of energy lost. But where is it gone? In this entire case, there was no friction, there was no air resistance. Where is that energy gone? And that is a perplexing kind of a question. But the answer is very simple if you think. Now, if you look at how a chain works, if you look at how a chain is and how a chain works, you will see that there are links, and one link will pull the link which is directly below it, and there will be a small amount of sound created, a small amplitude of sound created. There will also be a small jerk. There will be small deformations wherever the two links are hitting each other, and the energy will be lost in that sound energy, in the energy used up in deforming that steel chain, and so on. Even if there is no steel chain, if you were to lift a string up like this, there will be energy loss, because then there will be energy loss in the intermolecular structure, and there is no way that we can go away from this energy loss, because the equations, they show us this amount of energy loss. In fact, the actual energy loss in a real life process will be more than this, because you will have air resistance added up and so on. But this is the ideal case, so there is always some kind of energy loss in lifting up a chain like this.